So here we're looking at conjugate acid and base pairs and the formation of a conjugate substance from an acid or base. A conjugate pair is two species differing by a single proton. Please bear that in mind. That's such a useful tool to have at your disposal when it comes to questions. Conjugate acid-base pair differ by the presence of one hydrogen ion only. I could say proton, I could say hydrogen ion. When an acid donates a proton, it becomes a conjugate base. The conjugate base that it forms could regain the proton to reform the original acid. When a base accepts a proton, it becomes a conjugate acid. The conjugate acid it forms might donate that proton and reform the original base. In a reverse reaction, a conjugate base behaves like a base while a conjugate acid behaves like an acid. Let's look. In the example, HCl, an acid, donating H+, becoming Cl-. I see the reversible sign. What can happen is that Cl- can regain that H+ and go back to being HCl. It's the conjugate base of HCl. Going right back to the top of this slide, conjugate pair, two species, differing by a single proton. Yes, HCl and Cl-. NH3, a base, accepting that proton, going to NH4+, and that NH4+ is the conjugate acid. It can go back, donating that H+, which is what makes it an acid, and reform the base. My conjugate acid-base pairs from this example, HCl and Cl-, NH3 and NH4+. Conjugate pairs differ from each other by one proton. So, in which of the following reactants is the species in red behaving as a base? I've highlighted B because what is a base? A species that accepts a proton. CO3 2- is doing that. Next, which one of the following is the conjugate base of the hydrogen sulfide ion? It's going to be differing by one hydrogen only. If I'm looking for a conjugate base, HSO3- must be acting as an acid, must have lost its H+. If it's lost H+, the SO3- anion must become SO3- 2. D. If we're looking for a conjugate base, then the original substance will be losing a proton, will be an acid. So what is the conjugate acid of, and I've got 5 substances. Let's do all this at the same time. If I've got an acid and it donates its H+, the other product, A-, is the conjugate base. For example, CH3COOH acting as an acid, donating its H+, the conjugate base is the anion, CH3COO-. How do I get back from the conjugate base to its original acid, which I'm going to call the conjugate acid? I add a H+. So CH3COO- I becomes CH3COOH. HSO4-, I'm adding a hydrogen. The hydrogen's coming in as a H+. That means in this case it's 0. NH3, add the H plus gives NH4 plus. OH minus, add the H plus becomes neutral water. F minus becomes HF. And the conjugate base of the following substances. Looking at them, they all contain hydrogen. If I'm looking for the conjugate base, I must be taking away H plus. If I'm removing H plus, as in the first one, HCl, what's left is Cl, but it will be Cl minus. HCl gives us H plus and Cl minus to balance charge. H3O plus loses H plus, becomes H2O. HSO4 minus loses HH plus, and my charge has to go up now to -2. NH3 becomes NH2 minus. Conjugate acid-base pairs always differ by a single proton. Well worth remembering. Written structures should always make clear the approximate location of the proton that is transferred. This applies especially to organic conjugate acid-base pairs. Few examples. Ethanoic acid, CH3, COOH. When it acts as an acid, it gives off H+, and if I look where the negative sign is written on the anion, it's next to the oxygen that the hydrogen came from. Ethanol, C2H5OH. If that was to behave as an acid, H+ would form, and I see the negative charge on the resulting anion. The negative charge drawn on the oxygen atom that the hydrogen left. Phenol, C6H5OH. If it gives off H+, the negative charge is located on the oxygen, and that's where it's drawn. If an acid is strong, its conjugate base is weak. The stronger the acid, the weaker its conjugate base. The more the equilibrium lies towards the products. I have an equation. H2SO4 is a strong acid, making HSO4 minus a weak conjugate base. OH minus is a strong base. If it's a strong base, it makes H2O a weak conjugate acid. In the next equilibrium, CH3COOH is forming CH3COO minus. On the left we have the acid, on the right its conjugate base. The acid is a weak acid, the base is a strong conjugate base. A stronger base has a weaker conjugate acid. A weaker base has a stronger conjugate acid. Few quick questions to end with. Which of the following is not a conjugate acid-base pair? Remembering that a conjugate acid-base pair differs by one H plus C. The two options are differing by two H plus ions. Takes us straight to C. Such a useful rule. Explain using the Bronsted-Lowry theory how water can act as either an acid or a base. In each case, outline the conjugate acid or base it can form. If water acts as an acid, it gives off H+. It forms the conjugate base OH-. On the other hand, if H2O accepts H+, when it acts as a base, it accepts H+, it forms the conjugate acid H3O+. Two more. What is the conjugate base of the acid H2CO3? So, when an acid reacts, it donates H+, and differs from the conjugate base it forms by 1H+. The charge on the base becomes more negative by 1. B is my option, 1 hydrogen less, and my overall charge has gone from 0 in the acid that we begin with to the conjugate base that's formed. And what is the conjugate base of H2PO4 minus? The conjugate base will have 1 hydrogen less, and the negative charge increases by 1, and that takes us to B. That's it. If you found that useful, please hit like and please subscribe for more content.